Hey, what's up guys, Zol here, and I'm sure a lot of you have heard about, if you've been involved in the science community at all in the last couple of years, the James Webb Space Telescope. And even more so with the fact that it has been launched recently after years upon years and billions of dollars in the making. And in honor of that, I wanted to throw together this video about some of the cool chemistry behind the materials used in the telescope. Specifically, some of the materials used in the mirrors for the telescope are really cool and have some really cool properties, and I wanted to make this video revolving around the chemistry of those materials. The main one that I'm sure all of you have noticed is that NASA likes to throw gold on a lot of things. There's gold foil, gold on the telescopes, gold mirrors, and a lot of you know that gold is a really chemical resistant metal that doesn't like to oxidize, etc. And while that is part of the reason it is used on all of the space equipment, it is not the main one, and I want to go into the cool chemistry of gold and why NASA likes to throw it on absolutely everything. Now, the first thing you'll notice on the James Webb Space Telescope is the massive hexagonal mirrors that make up the main body of the telescope and how they are gold colored. Now, the main thing here is those are not solid gold mirrors that would be crazy heavy and crazy expensive, but that being said, they are still made out of a pretty cool material. The mirrors on the James Webb Space Telescope are actually made out of beryllium. Beryllium is the fourth element on the periodic table, and it is part of the group of alkaline earth metals. It is also one of the lightest metals, but despite this, it's extremely strong and really resistant to thermal expansion. This is really important on something like any aerospace equipment, specifically in a telescope, where you need really tight tolerances, and it's being put into space where there are massive temperature gradients from extremely hot to extremely cold temperatures. So it causes a huge issue if the materials you're using are going to change size and shape just based off these massive temperature fluctuations. This is why beryllium is mainly used in a lot of aerospace applications, because although there are other materials that are really good with temperature fluctuations and thermal expansion, most of those are very heavy, dense metals, and that makes them really hard to put up into space. Because of this, beryllium is used in applications like the main body of the mirrors of the James Webb Space Telescope. Now, these mirrors aren't just solid beryllium, they're actually formed with a really cool process where a fine beryllium powder is used and basically compressed down to give the mirrors their shape. What this does is it makes the mirrors even less dense because you're not using a solid amount of beryllium, and even lighter to be able to launch into space. The one caveat to working with beryllium is it's pretty toxic, and it can actually cause the body to have allergic reactions after repeated exposure, so you have to be really careful when working with it. After the mirrors are formed out of beryllium, they're then polished to an almost perfect mirror shine, and then the final coating is put on them. And that's where we get into the interesting chemistry of gold and why NASA likes to throw gold on absolutely everything. Now, gold, like most other metals, is a good conductor, and this has to do with a concept in inorganic chemistry called band theory. And this band theory and conduction are actually the reason NASA likes to put gold on a lot of their spacecraft. You see, in normal insulating materials, you have your valence shell and a conduction band, and there is a big gap between these. And as you move down to semiconductors, this valence band and conduction band move closer together, and this means with semiconductors, at least, they're still insulators unless you dope them with another material that turns them into conductors. With metals, on the other hand, you have actual overlap between your valence and conduction band, and what this allows the electrons to do is to be free-floating and basically traded between all the atoms in a group of a bunch of metal atoms. This is why you see electrons in the metallic groups have electron configurations of the metallic C as opposed to the normal ionic and covalent stuff that we see in normal chemistry. This metallic C is what gives metals a lot of their cool properties, because with all these free-flowing electrons and all these metal atoms just bundled together, it allows them to be a lot more ductile and flexible, and it also means since the electrons can just flow through, that's what gives metals their conduction, because electrons can easily flow through them, as opposed to with normal covalent compounds in the non-metallic range of the periodic table. Now, you may be asking yourself why NASA wants their aircraft and spacecraft to be covered in this gold foil that's extremely conductive. And it's not actually because it is conductive, but the same reason that metals are so conductive is also what makes them really reflective. You see, what happens when a light ray or other sort of energy wave comes in and hits an atom is it causes energy transitions into an electron, and it causes that to shoot off a similar energy wave in the same direction. Because of this, and because of this electron sea in metals, you have a lot of free electrons just floating around in this electron sea. So you have, when the light rays come in, you always have electrons there to help grab them and bounce them off. And with all these free-flowing electrons, you see, in the same way that gold and silver are extremely conductive, they have a lot of these free-flowing electrons in their electron sea. They're also extremely reflective metals because they have all these excess electrons able to grab and shoot off light. You actually see silver, being the most conductive metal, is also the most reflective of the metals, which is a really neat correlation between reflectivity and conduction. With gold, and for NASA's purposes, gold, the way that its electrons are arranged, it actually reflects infrared light the best. And since you don't have to worry about stuff like air and convection, the best way to insulate in space is to insulate against radiative energy, and so being able to insulate against infrared is really important on a lot of these spacecraft, which is why NASA uses gold instead of other materials, because gold is especially good at reflecting these infrared because of its electron sea. On the James Webb Space Telescope, it is a similar reason. Gold's extreme reflectivity is really good for the mirrors on the Space Telescope, and really good to get high quality images, and necessary to get high quality images on the telescope. So that's one of the main reasons NASA actually uses and sticks gold on a lot of their spacecraft and imaging equipment, is gold's unique reflective properties, both for normal visible light and infrared, along with, of course, being corrosion resistant, although that is less important in space because there is, of course, no air. Now, I hope that was some interesting facts about NASA's spacecraft and the recent James Webb Telescope launch. And if you liked the video, be sure to let me know and comment down below any other thoughts on cool chemistry that NASA does. I'll see you guys next time.